Alright, good morning AP Chemistry. This is Chapter 8, and this is going to be general bonding concepts. Most you've been exposed to before, and some of them you have not. So Section 1 is called Types of Chemical Bonds, which you have been exposed to. This is, of course, going through the chemical bonds that are possible in compounds. For example, ionic, covalent, polar covalent, non-polar covalent, etc. So this part you've had before. All right, let's do some definitions. Definition, what is a bond? A bond is a force that holds atoms together as a unit. That's a pretty big definition because it covers a lot of territory. That does not only just cover compound bonds, but don't forget the diatomics are actual like atoms bonded to each other. So that bond can be a lot of different options here. The main goal of bonding is to achieve lowest possible energy. Again, an underlying theory of chemistry, an underlying principle is the lowest possible energy is better. Bond energy is the energy required to break a bond and informs us about the strength of the bond, which of course the more energy to break, the stronger the bond. All bond energies are technically positive. It's the change in enthalpy between breaking the bond and making the bond that's potentially negative. Bond length is the distance where the system energy is at a minimum. This one's kind of important. Your length of your bond will be determined by what the lowest energy is. And I've got a pictorial I'm going to show you in a minute. The enthalpy is the broken bonds minus the formed bonds. And again, you can have the possibility of a negative value for your enthalpy, especially if the energy to break the bonds is a smaller number than the energy required to make the bonds. Change in enthalpy between breaking bonds, absorbing or a positive value, and making bonds released or a negative value. So the broken bonds are technically going to be your reactants, and the formed bonds. So your broken bonds are technically your reactants, and your formed bonds are technically your products, because of course in order to make products you have to break the bonds of the reactants. Notice this is the first time where it's not final minus initial, products minus reactants. This is the only situation where it's actually reactants minus product energy. Alright, so this is a little pictorial. This is the formation of the bond between two hydrogen atoms to form hydrogen gas. And what I want you to realize is the lowest energy is the better. The bond distance here is even lower energy than really close here. So low energy, better, and the energy dips down. This is the perfect length for the bond between the two hydrogens. Anything else is too high energy. Anything else is too unstable. So it is the optimum distance for low energy. This one does not even cut it. Even though they're bonded, even though they're nice and tight and close, it's still not good enough to be the lowest energy. Alright, there are three basic types of bonds which you should know from first year chemistry. Ionic, which is the electrostatic attraction between ions. Any ionic compound is an ionic bond. And then you have your covalent, and the two types of covalent is polar and nonpolar, and covalent bonds are sharing of electrons. Alright, Section 2, electronegativity, not to be mistaken with electron affinity. And Section 3, dipole moments. Alright, the definition of electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. The difference between electronegativity and electron affinity is that electron affinity is a standalone atom. Electronegativity is in a compound. If the attraction for the electrons is equal between the two atoms in the compound, it will be a non-polar covalent bond. If the attraction is unequal, it's either a polar covalent bond or an ionic bond, depending on the size of the electronegativity. Now, these are bonds, mind you, not to be mistaken with polar molecules, which we will discuss. The larger the difference in electronegativity, the more ionic the bond is going to be. And we are going to figure out the difference in electronegativity between the two atoms that is in the compound forming the bond 3 different ways. One of the ways you are quite familiar with, that's trend on the periodic table. A second way is if you are given the actual electronegativities of the 2 atoms in the bond, you're going to calculate, literally calculate the difference in electronegativity and figure out the type of bond it is based on that. Or percent ionic character, which is just a definition, which I just said. We are mathematically going to compute electronegativity given the electronegativities of the 2 elements involved in the bond, or just go by trend, which is the one we use most often. And the trend of electronegativity on the periodic table is generally, and you got lots of exceptions for electronegativity. That's why a lot of times, if you calculate it mathematically, given the electronegativities, and you do it based on your trend on the periodic table, there are some discrepancies. But again, you're not going to memorize all the electronegativities of every atom on the periodic table, so we can live with some of the discrepancies. So generally, increase going across, decreases going down. And this is just kind of this is again the ability of the atom in a molecule to attract shared electrons to itself. It's just what it is. And of course, you would expect that to be higher in the upper right, which it is. Increases going across, increases going up. So it is higher in that upper right-hand corner. All right, if you are actually given the electronegativities, and they would have to be given to you in order to use the mathematical computation, you would do a difference in electronegativity, big number minus a small number, and you would get, if it's nonpolar, it'll fall between the 0 and the 0.4 range, polar 0.5 to 1.9, ionic 2 and up. Placement on the periodic table, that's the trend, the one we use the most, and again the trend is increasing going across, decreasing going down the table. And the third and final one is really just a definition. There is a computation to go along with it, but we don't tackle that. It's not that important to the concept, and that's called percent ionic character. The computation is in your book if you want to look at it, but I've never come across it other than a definition. And the percent ionic character of a bond, 50% or more, is going to be considered ionic. So 3 ways of electronegativity. We usually use position on the periodic table most, and then the second way we'll use the most is by calculating it, and falls into one of these characters. And I'm going to do an example for you. Okay, so here's a quick example, and I'm going to do another one where it's actually a discrepancy, but this one's not a discrepancy. HCl, hydrogen is technically a nonmetal, chloride is technically a nonmetal. From first year chemistry ages ago, you already learned that this is going to be a covalent bond and not an ionic. Why? Because both of those are technically nonmetals. The electronegativity of chlorine is equal to 3.16. The electronegativity of hydrogen is equal to 2.20. If you're actually given the values for both of those elements in the bond, then you're going to calculate the change in electronegativity and determine, sorry, that should be En, and determine the polarity or non-polarity of the bond or the type of bond from that. So in this situation, I'm doing it both ways. Based on position on the periodic table and previous knowledge from first-year chemistry, HCl should be a covalent bond. And the fact that hydrogen is on the left, chlorine is on the right, and that electronegativity increases as you go across, and of course that whole corridor, that oxygen, fluorine, chlorine, nitrogen corridor has high electronegativities, I would assume that since it's covalent, I'm going to assume that hydrogen and chloride have different electronegativities, and that chlorine has the higher electronegativity. The electrons are scooting towards the chlorine, and that's making it more negative. So the bond itself is going to be a polar covalent bond. The second method of determining the difference in electronegativity is actually calculating the difference in the electronegativities. You can only do this if it's given to you. You can't memorize all the electronegativities on the periodic table. That would be a nightmare. So the difference in electronegativity between the chlorine and the hydrogen is 0.96, and based on the chart previously given, that's still going to be a polar covalent bond. So that's one example. Alright, so this is going to be one of those discrepancies. But in a situation like this, you're still going to call it an ionic compound. Based on prior knowledge, potassium iodide, left side metal, metal heads are losers, iodide, right side gains. You have an electrostatic attraction because this is a loss or gain of electrons. You would call this a ionic bond and an ionic compound. Now, given the electronegativities of potassium and iodide, there's going to be a small discrepancy. If you do the difference in the electronegativities, and they have to be given, again, you will never memorize all these electronegativities. It's impossible. They will have to be given to you. If you're doing the difference in electronegativity, 2.66 minus 8.2 gives you 1.84, and based on the chart, a polar covalent bond is 0.5 to 1.9. Based on the chart, this is actually going to come under the category of a polar covalent bond. So there are definitely discrepancies when you start messing with the calculations of electronegativity differences. Non-polar covalent bonds, the electrons are shared equally. There's no dipole moment. Molecules will always be non-polar. A dipole moment is, again, a bond where the electrons are attracted to an atom more than another, where the electrons are scooting closer to that atom, creating a negative end there, and since it's moving away from the other atom, creating a positive end at that side. Polar covalent bonds, our electrons are shared unequally, may or may not create a polar molecule. That's going to be for future purposes when we start doing geometry. You can have a polar bond and a nonpolar molecule, but you can never have a nonpolar bond and a polar molecule. So right now we're still just discussing bonds. And the two types of covalent bonds are staring you in the face, and of course you already know what an ionic bond is like. All right, again, to just bring it on home, a dipole moment. Fluorine has a larger electronegativity than carbon, based on both position of the periodic table and the electronegativities. All right, so here's an example. Carbon has an electronegativity of 2.55. Fluorine has an electronegativity of 3.98. Carbon and fluorine are both considered nonmetals, so you would categorize this based on position of the periodic table as a covalent bond, which is correct. Then you'd have to think to yourself, okay, is it nonpolar or is it a polar covalent bond? Based on the position on the periodic table, fluorine, and of course fluorine has the largest electronegativity of all the elements on the periodic table. Fluorine has a large electronegativity, therefore this bond is going to be polar. That gets confirmed by the difference in electronegativity between the carbon and the fluorine. What you have created here is a dipole moment because you have a bond that is more positive at this end and more negative at this end. And again, we're still talking bond. Let's not get into the molecule till later. So the bond is a dipole moment. The bond would adjust itself, align itself to a particular matter in an electric field. So this is called a dipole moment because it is a polar bond. And that's a brief one on electronegativity.